Okay, next up is conservation of mechanical energy. And we're going to hook it into the conservation of momentum. But first we have to talk a little bit about what is mechanical energy. You learned what it was in grade 11, but I know that grade 11 physics could be a long time ago now, so you may not remember it. Okay, mechanical energy for us is made up of three different types. It's made up of gravitational potential, which we write as capital E with the subscript G. Remember, all of our energies are always capital E's with subscripts telling us the type. So this is gravitational potential. And remember, potential energy is any energy that's stored in an object. And the way you can tell if something has potential energy is release it and see if it'll move. So if I lift something up into the air and I'm holding it there, maybe I'm on the roof of the building holding this random object out over the edge, and you can imagine who that would be. And you're like, oh, does he have gravitational potential energy? And I let him go and he falls, and of course he does. Hopefully you remember that gravitational potential energy is equal to mgh. It's the work done against gravity to move an object to some height. Work is mg and h is the height. So that's gravitational potential. In the last video, when we were talking about is it elastic, we used EK. It's kinetic energy. And that's energy of motion. So if an object is moving, then it's going to have kinetic energy. And kinetic energy is equal to 1/2 mv squared. And then the third type of energy that we used last year was the energy found in springs and things that stretch. And it's EE, and it's called elastic. Elastic potential energy again. It's a potential energy because if you stretch it and then release it, it's going to spring back together. Or if you compress something and release it, it's going to spring apart. So it has, again, the potential to move when you release it. And it's all based on the property of an object, how much stretch it has. Okay, so we're thinking like a spring, a slinky, the springs and the shocks of your car, but also maybe some clothing that has some spandex and stuff in it, has some elasticity, a rubber band. Okay, and elastic potential energy is equal to 1/2 kx squared, where k is the spring constant. And it tells us about how stiff or how light a spring is, how difficult it is to stretch or not, will be dependent on the spring constant. So the spring and the shocks of my car would have a really big K. It would be really huge, which would make the elastic potential energy large. The spring in a click pin would be really tiny K, have a really tiny K, and it would make the elastic potential energy tiny. Remember, this equation is connected to Hooke's law, F equals kx, where F is the force you have to put on a spring to stretch it, K again is the spring constant, and the x in both of these cases is how much you have stretched or compressed. It's a distance. So distance stretched or compressed. So obviously the bigger the K, then the easier it is, or the harder it's going to be to stretch. The smaller the K, the easier it's going to be to stretch. Okay? And again, bigger K, more elastic potential energy, smaller K, less elastic potential energy. The one other energy that we used last year was E lost. And if you remember, E lost was always the work done by friction. Because it's the E lost is usually the energy the object has lost by sliding across the surface. And we know work done is equal to F delta D cos theta, where the F is friction. So it'll be FFR delta D cos theta. And of course, if it's on a level surface, whether it's on a level surface or not, FFR is mu Fn delta D cos theta. So we could find the mu. If it's on a level surface, the Fn would just be mg. but we usually write it as this until we know what they're asking for, because sometimes the question asks for the force, sometimes it asks for the coefficient. Okay, and so then that leads us to our conservation of mechanical energy, which hopefully now you maybe begin to remember, and it is the total kinetic energy of an object initially, plus its total gravitational energy initially, plus its total elastic potential energy initially, is equal to the total kinetic energy after whatever it is that's happened, the event, plus the gravitational potential energy after, plus the elastic potential energy after, plus whatever energy got lost. Now, we don't use this in a collision. If it's a collision, we use momentum, because momentum is always conserved. We use this when there's a change in height or a change in speed or something's getting stretched or compressed. So we would use this if, remember last year, there was a kid on a slide. And so the kid was sitting up here with an initial speed of 0. And the height is maybe, I don't know, like let's make it a fun slide, 10 meters high. And we could find the speed of the kid at the bottom, the VF. Remember us doing this? So we would start out with 1/2 mv initial squared plus mgh initial 1/2 kx final squared. And then it's equal to, that just looks like a plus sign, 1/2 mv final squared mgh final 1/2 kx final squared plus the E lost. So our slide is frictionless and there's no spring. And so then we say, okay, initially up here at the top, the kid's stationary. He's sitting there waiting for whoever to clear the slide. But he has some height, so the mgh stays. And then at the bottom, he's at the bottom. There's no height, but he has some speed. And so we're left with mgh initial equals 1/2 mv final squared. The m's will cancel, and we're looking for the speed at the bottom. Multiply both sides by 2. So v final squared will equal 2gh initial. 2 times 9.81 meters per second squared times 10 meters. Don't forget to take the square root, and when you do, you get 14.007 meters per second. Okay? So this is a question straight from the grade 11 course. So why the heck are we doing this now? Well, we're doing this now because now we're going to combine this change in energy with the conservation of momentum. So now this kid that's sitting at the top of the slide, he doesn't notice, but there's a kid sitting at the bottom. And so when this guy comes down with this speed, he's going to smuck into the kid at the bottom. And when he smucks into the kid at the bottom, then they're going to careen off. So the question would become something like, so I'm just going to redraw. So the question would have a kid sitting up here, a kid sitting down here, and then this one's going to come down, is going to smuck into this kid. They're going to get entangled, and they're going to go sliding across the playground for some distance. And the question might be, what must be the coefficient of friction if they eventually come to a stop? Let's say 10 meters later, we may as well make it a good ride. So from the previous question, we had this height was 10 meters high. We had the kid up here is stationary to start with, and so is the kid down here before he gets smucked. Let's make this guy M1 be 50 kilograms. And let's make M2 be 40 kilograms. And the question's going to be, then what must be the coefficient of friction if they eventually come to rest 10 meters later? Okay, so there are parts to this question, and we're going to run out of time. So we'll come back in the next video and solve it, okay? I'll just hold it here so you can draw it for the last 4 seconds of the video.